So we've treated from week 1 up until week 12. And here in week 12 would be treating the topic called electrolysis and electrochemical cells. So we'll also touch fuel cells and battery cells. So let's head into the lesson. First off, I would start by an introduction to electrochemistry. So can you guys hear me?
Yes, sir.
Yes, sir.
Okay. Okay, so let's go. So electrochemistry is actually that branch of science that deals with the study of how electrical energy is converted to chemical, or how chemical energy is converted into electrical energy. So that's the study of this is called electrochemistry. So as I have it here, I said electrochemistry deals with the relationship between electricity and chemical reactions. So it involves studying the processes where chemical energy and chemical energy is converted to electrical energy and vice versa. So when we hear electrochemistry, there are two things that always happen in every electrical, in most of the branches of, it's not most of, generally in electrochemistry, you are either moving from chemical to electrical or from electrical to chemical. So the study of this process is what is known as electrochemistry. It's the study of the process of chemical energy being converted to electrical energy and electrical energy being converted into chemical energy. So for this lesson today, we'll be treating electrolysis. I'll try to explain what electrolysis is, and also electrochemical cells, what they are, then fuel cells and batteries. So first off, what is electrolysis? Electrolysis is, as I have here, is the process of using electrical energy to drive a non-spontaneous chemical reaction. So what does this mean? So some reaction, when you hear that a reaction is spontaneous, it means that reaction would happen without any extra applied force. Just putting, like now you have say um we have salt, dropping salt inside water. The dissolution is spontaneous. That's for salt to dissolve into water is spontaneous because you don't need to apply any extra pressure or any external force to make um, salt dissolve into water. But in the case where you have something like maybe camphor to dissolve camphor inside water, you would actually need to heat it up to a point where both of them will be able to be compatible enough and the camphor will dissolve. Or even using sand in water, if you pour sand in water, it will not dissolve. It will not dissolve. It's only dust particle that probably will stain the surface of the water or stain the water's appearance. But the sand itself would not dissolve. So before you can dissolve sand in water, the water itself will even evaporate because for you to be able to keep sand in water or melt sand, the temperature needs to be very high, around 400 degrees Celsius, if I'm correct. So to melt sand, then you will start thinking of now pouring this or letting it dissolve into water. So spontaneous reactions are reactions that they occur by themselves without any extra force. So electrolysis is actually done. It's actually a process that is done to cause all these non-spontaneous reaction to cause the what they call it, the transfer of either chemical to electrical or electrical to chemical that will not happen spontaneously. So that's electrolysis. So from my slide, I said it's a process that is using electrical energy to drive a non-spontaneous chemical reaction. So electrochemistry, electrolysis in real sense or in a simpler term, it's trying to charge two metals, or descriptively, you take two metals, you pass high voltage current through them. Then once you've passed high voltage current through them, you put these two metals inside a particular solution. So when you put it into the solution, normally, if you put only the metal into the solution and connect just wire, nothing will happen. But now you need an external force, like a voltage source, that will then power these batteries and cause the reaction between the solution that you put this sorry, not batteries, this rod or these metals, that will cause these metals to react to the solution and then allow for transfer of, or allow for any form of chemical reaction. So that's what
Excuse,
electrolysis is in.
excuse
Okay.
me, sir. So you
Yeah, I'm
said
listening.
it's using electrical energy to drive a non-spontaneous chemical reaction. Can you explain the meaning of that driving the sentence?
Explain the meaning of what drive.
Yeah,
Okay. The drive that they're talking about is just to kickstart a chemical reaction. To kickstart a chemical reaction. Because what happens, let me give a typical example of electrolysis. When you have, I don't know if you guys probably tried this thing personally, or probably in your school, maybe they did experiments. If you take pencil, that lead inside pencil, take two of it and connect any wire, flexible wire, all this, especially flexible wire, especially all those wire that have plenty mouths, and it looks like I see the brush that is inside the wire. Just tie that brush on one of the pencil, take another wire, tie on the other pencil stick, then pour salt inside normal water, pour salt inside that normal water, and put inside a container. Put these two pencil stick inside the same salt water, then connect the wires together. Don't put any battery yet. You will see that nothing will happen. The pencil will just stay there. Even though they are connected together, the pencil will just stay there. Nothing, you will not notice any change. But for you to now cause electricity to happen, for you to cause, because electricity, they say it is using electricity to drive a chemical reaction, that is to force a chemical reaction to happen. So now you just take this same wire that you tied, the two ends of the wire that belongs to the first pencil and the second pencil, joining them together alone without a battery, you will not notice anything because the reaction is not spontaneous. But when you now detach this joined wire and put a battery to this wire, anyhow, whether you put one on the positive, just put it together. You can use your hand. It will not, the electric voltage is not really high. Just place it together. You will notice immediately on each of the pencil, you will start noticing bubble will be coming out like as if the water is boiling. Bubble will start accumulating on the body of each of these pencils as they dip into this salt and water solution automatically. So now, what is now happening there is it is causing chemical reaction inside the salt. It's causing the salt particles to dissociate and move towards the candle of the pencil sticks with different charges, with opposite charges. So now, what has happened is that you've used the electrical energy of the battery to force chemical reaction, the dissociation of the sodium chloride molecules inside the solution, the proper dissociation and separation of these molecules. So that way, you've used electrical energy to drive this chemical process. So I don't know if it's clear now.
it is, sir. Thank you.
Okay, you're welcome. So now, this electrolysis, it requires an electrolyte, which is an ionic compound, and two electrodes, which is anode and a cathode. So now, when you are trying to set up an electrochemical system or electrolytic system, you would always need an electrolyte, connecting wires, electrodes, and sometimes you may need what it's called a salt bridge or an ion exchange or an ion exchanger. So this is typically the normal setup for most of these electrochemical cells, but electrolytic cells, they don't really need that salt bridge because electrolytic cells, they use battery to power the reaction. But a normal electrochemical cell, which sometimes they call it galvanic or voltaic cell, you don't even need to put a battery. That one is not electrolysis because that one, you don't need a battery. Those ones are spontaneous reaction that we're just putting these two, connecting them in a way they will cause automatic instantly the chemical reaction will start happening because you've connected the wires together. There will be a swap of electrons and so on. So those kind of ones, they're not really under electrolysis. They are generally under electrochemical reactions, but they're not under electrolysis. So there are two things when you talk about what they call it, chemical reactions. There is the one that is involving chemical reaction to generate electricity and electricity to generate chemical reaction. So the one that is involving electricity to generate chemical reaction is what is known as electrolysis or electrolytic cell setup. I don't know if I'm communicating at all.
Yes, sir. You are.
Does anybody have any question?
Excuse me, sir. Please don't be offended. I know I just joined. Please, can you come again with that practical demonstration of electrolysis? Thank you.
Okay, for electrolysis, what happens in electrolysis is for you would need electrodes, two electrodes at least, two electrodes. Then these two electrodes would need to be immersed in an electrolyte. Then once they are immersed in an electrolyte, they could be separate electrolytes, but they could be the same electrolyte, but sometimes it's the same, but sometimes they are separate. But there will always be need of of electrodes and electrolytes connecting wires. And for electrolysis specifically, you would need a battery. If you're not talking about electrolysis, you don't need a battery, because in electrolysis, it involves converting electrical energy, that is the electricity from the battery, into chemical reaction, which is the thing you are seeing in the electrolyte solution. So that's what electrolysis is about, converting electrical energy into chemical to force chemical reaction. So I was trying to give an example saying, if you can try the experiment in your house or anywhere. Just take a, even if it's cover of, and what they call it, not really cover, just a small container, very, very small. No, it doesn't need to be very big, just something that is transparent that I can see. Take pencil lead, two, or break one into two, make it long, a bit long enough. Then dip these two pencils inside this water that is in the small container. The water, pour salt inside the water, like salt, just stir it and pour salt inside. Put the two pencils inside without connecting their wires. You will notice that nothing happened. The reaction is not spontaneous. Then say, okay, maybe what will happen is you connect each of the pencil leads with wire, all this flexible wire that looks like brush. The wire inside is not just a thin metal, it's plenty brush mouth. Tie it on the heads of each of the pencil, then connect them together. You will see that nothing is actually happening because the reaction is non-spontaneous. So now, to force the reaction to happen, now you would then, that place that you joined the two wires together, instead of joining them together alone without a battery, just disconnect them and put a battery in between, positive end on one side and negative end on one side, and connect it. Immediately, you would see an electrolytic reaction occurring. You'll be noticing bubble on each of the candlesticks, sorry, each of the pencil sticks. You notice bubble live, like it will happen without, it will not shock you. It's not going to shock because it doesn't have enough voltage, it's battery. So immediately you start seeing the exchange of electrons on the surface of the rod in form of bubbles. So this is an example of electrolysis in action. So electrolysis, in another word, is using electricity to break components in a particular solution or to force chemical reactions. So I don't know if it's clear.
Very clear, sir. Thank you very much.
Okay, you're welcome. So as I was saying, you have just some major parameters that you need every time you want to set up an electrolytic cell or an electrochemical cell. You need electrodes, electrolytes, connecting wire, electrodes, electrolytes, connecting wire. In some cases, you might need an ion exchanger or a salt bridge. In some cases, you might also need a battery, but it's not always necessary. But the major thing that you would always need in every electrochemical cell is electrodes, two electrodes. You always need an electrolyte. Then you will always need connecting wires. Most of the times, like I would say 80% of the times. Because recently you might not really need the connecting wire. Sometimes you might just need them to be connected, but the two electrodes needs to be connected in a way. So that's the idea. So that's why here you can see that I'm just mentioning only electrolytes and electrode, because these ones, they don't remove. No matter what is happening, there's nothing that you can do. You would always have to have electrodes and electrolytes for you to have any electrochemical cell. So now they are used for extracting metals, they're used for electroplating, and they are used for production of chemicals like chlorine and hydrogen. So when that pencil experiment I was talking about, where I say you have water in, or what they call it, salt and water inside, and you have a pencil, or you have two pencil leads dipped into this water salt solution. On one of the electrode, on the positive, the electrode that is tied to the positive side, the bubble that you are seeing on the body is chlorine gas. So this is an example of how you can use electrolysis to generate the formation of chlorine gas. So in industrial level, they would try to gather this gas so that they will not just waste in the air, but the gas would now be collected. If you want to try it personally or by yourself, you might not really notice quantity, reasonable quantity, because you're doing it small scale, but you will notice the bubble. Definitely, you will see that the thing is like as if something is boiling, like as if you dip boiling ring into this water, but it will not be hot. but it's just what will happen. So now, under electrolysis, there are laws that kind of governs electrolysis. And the laws that govern electrolysis is Faraday's law. Faraday's law. So this Faraday's law could be grouped into first law and second law. First law of Faraday's electrolysis and second law of Faraday's electrolysis. So for the first law, it says that the amount of a substance deposited or dissolved at an electrode is directly proportional to the quantity of electricity passed. So what does this mean? It means when you have, like this our salt system now, the amount of chlorine bubble that will be formed on the positive electrode, the amount of chlorine bubble that will be formed on the positive electrode is dependent on the charge of the battery that you're using to power the system. That's what this first law is trying to just state in summary. That as the battery increases, it means the amount of chlorine that will be generated will be increasing more. So it will be increasing. So that's what this first law is stating. It's stating that the amount of substance deposited or dissolved at an electrode is directly proportional to the quantity of electricity passed. So for the second law says that the amount of different substances deposited by the quantity of electricity is proportional to the equivalent weight. So what this one is just trying to say is trying to now use both sides. Like on the first law, they're trying to focus on just one electrode. But now on the second law, they're trying to talk about generally the amount of every substance that is deposited by a particular amount of electricity is proportional to their equivalent weights. So just like as if it's kind of like trying to talk about the first one was talking about one, the second one is trying to talk about in general. In general. So there's a relationship like that. So for the first law, there is a formula that states that M is equal to M times Q over NF. M is equal to MQ over NF, where the small letter m is representing the mass, capital letter M is representing the molar mass, then N is representing the number of neutrons, not number of moles, number of neutrons. So, and F is representing the Faraday's constant, which is 96485 or 96500. So in some places you see it as 96500, in some places you see it as 96485. So 96,500. In some cases, that's the Faraday's constant. So now before I move forward, I said that you would always have an electrolyte and you always have an electrode. So there are two types of electrodes, positive and negative electrode. So now, if for something I would have said, if not for something I would have tried going into details about the changes that happen to which electrode is called anode and which electrode is called cathode, but it's not really for basic level chemistry, so it will not get confusing. But just know that the anode is always known as the positive electrode. It's generally, most of the times, it's known as the positive electrode, while
Please,
the cathode is known as the negative. Yeah.
so please can you re-explain the second law of Faraday?
Okay. The second law is stating that the total amount, that is the amount of different substance deposited by the same quantity of electricity. That means, um, let's assume you pass in, let me say, a particular quantity of electricity. The amount of each of the substances now, you say, let's assume you have A deposited, B was deposited. So you're saying that that amount of A and B that were deposited has at the same electricity quantity has a relationship with their equivalent weight. So now you're talking about amount deposited, the relationship between amount deposited and the weight of particles deposited. So just like I said,
Okay,
I try to say
thank you.
that the amount of a particular, is it clear now?
Yes, sir.
So the second law is talking about the amount deposited having a relationship with their equal weights or their equivalent weights or their weight at equivalent or at equilibrium or something like that. So now moving on, let's see an example of this first law in action. So for example, we have calculate the mass of copper deposited when 5 ampere of current is passed for 1 hour So this formula is what is supposed to be used. This is our formula that we have here. But now we are now introducing what they call it. We are now introducing current and time. So another formula that you should take note of is the formula that says that Q is equal to IT. That's the normal formula for quantity of charge. Quantity of charge is always equal to IT. Q is equal to IT. So the quantity of every of charge is always equal to IT. Q is always equal to IT. So we also have that M is equal to MQ all over NF. I've explained what they mean. So now from the question, they gave us copper. So the molar mass of copper is 3.5 constant. The answer, the mass of copper deposited when, calculate the mass of copper deposited when 5 ampere of current is passed for 1 hour through a copper sulfate solution. So now, since we are giving current now, we are not giving the quantity of what they call it, of charge. We're not giving the quantity of charge. That is Q here. We're not giving the quantity of charge here. We have the molar mass of copper is 3.5. We are asked to look for our small m. We can get the number of electrons, normal reaction, how copper reacts. Because when copper reacts, every time, copper is a divalent element. So when it reacts, it always forms mostly copper 2 most of the times. Copper 2 is the most prevalent copper this thing. So it has a positive charge of +2 almost every time. So that's the number of this thing. That's the number of electrons. 2. So for the Faraday's constant is a constant. So we could have used this formula directly, but just that we don't have our Q. We don't have Q. So to get Q, we know that there's a formula that says that Q is equal to IT. So since Q is equal to IT, they gave us current and time. We can use I and T to get our Q and substitute it in the major formula. So multiplying I and T, which is what we did here. I and T. Our I is 5 ampere. Our T was 1 hour. So 1 hour, we convert it to SI units, because as I always advise, it's best we always leave our answers in SI units, except in those cases I have mentioned previously in my classes where I said, okay, in this case, it's preferable that you use this unit, or if you are not changing this one, don't change that one, those kind of stuff. Those rare cases are the cases where you leave your SI unit without paying attention to it. But normally, you're supposed to always change your units to SI units, except they asked of any other units from the question. So now in this case, now we just multiply our I by T. So to get how we got the 3,600 was 60 seconds make 1 minute, 60 minutes make 1 hour. So we have 1 hour. So 60 seconds times 60 minutes is going to give us the amount of seconds in 1 hour. In 1 hour. So doing that, you will get 18,000 coulomb as the quantity of charge. So that way we can then substitute it into this formula here, and we'll get our answer. I don't know if you guys can still hear me.
Yes, sir, I can hear you.
Okay. So that if you plug everything and play perfectly, you should be able to get your answer as 59.2. So you could try it so we'll know whether our answer is actually correct. So normally your answer is supposed to give you 59.2 grams as the mass of copper that will be deposited for 5 ampere of current for 1 hour. 1 hour. So let's hope that you guys will do it and confirm your answer while we try moving forward. So moving forward, we have what is known as the electrochemical series. The electrochemical series. So this electrochemical series is a list of elements. The list of elements or compounds arranged according to their electrode potential. I don't know if you
Excuse me,
guys
sir.
got this.
Excuse
Yeah.
me, sir. Sorry to take you back to the question. Please, how did you get F?
How did I get
F,
F?
yes.
The F is a constant. Faraday's constant.
Okay.
96500.
Okay.
So now we are on electrochemical series. So now this electrochemical series, they are a series that show um, the elements with their increasing number of electronegativity. I think I supposed to send a this thing, a what they call it, a list that would arrange them in order of increasing order, arrange in increasing and decreasing order. Let me see whether I can send it to the group. I'm coming.
Hello?
Yeah, I can
So
hear
you
you.
said that NO represent what?
N, M. Okay,
Eh?
N.
NO?
N represent the number of
Small
electrons.
n. Number of what?
Electrons. See here. Number of electrons.
Okay.
I think maybe at the end of the class, I would send you guys the list so that we will not take. Okay, I think I've seen it here. I've seen it. So I'll be sending it to the group now so that it's just a small list. I think I see questions on this coming out most of the time. Let me see. Sending it to the group, right? Yep. So it should be on the group now. Okay, so I've sent it to the group. You will see a list of ions based on their increasing electronegativity. Based on their increasing electronegativity. So they said the ability to gain electrons and the ability to pull electrons. So if you're talking about based on the ability to pull electron, you start from fluorine. Fluorine is stronger to pull electron. It's highly electronegative. It's a highly electronegative. But now if you're trying to talk about the one that has the highest ability to give off electron, you start with magnesium. So either way, depending on what they're asking you, actually you arrange them
Please,
in
sir,
whatever.
come again. I didn't get you. Sorry, sir, for dragging you back, please.
Okay. So the list that I just sent to the group chat, the order that is arranged in an order where it starts from the one that has the highest tendency to give off electron. So if you look at it, the list starts from magnesium going to fluorine. So if you are looking at that order, it's showing that magnesium has higher tendency to give off electron compared to other ones. So while if they're asking for the ones with higher tendency to accept electrons, or the one that has highest electronegativity, you would flip the whole series, starting with fluorine, next oxygen, then chlorine, bromine in that order. Because this one is ability to give off. The order that I showed you is the ability to give off. But the other reverse order is ability to accept. So that's just it, Sha. So that is a typical example of the electrochemical series. So it's always constant. It's always a constant, and I think it's important that we just memorize it. Just even if you don't memorize so much about it, just look at how they are being arranged. Probably form an acronym for it so that you'll be able to remember. to know which one comes before which one and the
Okay.
order of
Still,
arrangement.
I didn't understand you. You are too fast.
So the fire arrangement is not showing on.
I said the electrochemical theory. Have you put one and sent to the group?
Sir?
You said that as you sent it, the list, the list is based on their increasing what? Let me understand that one first.
In, increasing ability. That is, it is based on, it's arranged such as the strongest to give. I mean, the one that has high ability to give. The only which word would I use now? The Father Christmas. The other is giving us. Father Christmas is magnesium, the one that gives a lot. Then the stingy person is fluorine. So you just take it like that. The Father Christmas is the one that is magnesium. So the next Father Christmas is going to be the one that is following magnesium, going down to the most stingy, fluorine. So fluorine being most stingy is it that has acar gum. And acar gum will be able to draw as many as he can to himself. So if you should reverse it the other way, the ability to be stingy or draw electron is going to be the one that is the strongest, that has the strongest ability to draw electron is fluorine. Next, chlorine. Sorry, next oxygen, next chlorine, then bromine in that order. I don't know if it's clear now.
I didn't get it. You are fast.
Okay, see what you just do. On your book, just write magnesium can give electron more than it can collect, while fluorine can accept, sorry, while fluorine, okay, just be like magnesium gives more electron, receives less electrons. Then for fluorine, gives less electron, accepts more electron. So just put it like that. Magnesium gives more, collects less, while fluorine gives less and collects more. So that way now, I think that way it should be able to explain itself. So now, moving on back to where we were, I think we've passed this point. So now I was talking about the electrochemical
The
theory. I said
definition now, the definition you gave now, hey, the definition
I'm,
you gave, you said the highest tendency to give off electron.
okay,
Just give me the definition and then the
just
ability to draw.
hold on. Just hold on. Once we continue in the lesson, it will become clear. Just hold on. I was trying to just gather everything all at once and dish it out, but just hold on. I'll take it gradually. So
Excuse
now,
me,
the
sir.
electrochemical,
I have a question.
I think, yeah.
I think my mic said the background is noisy, so that's why she's not getting what you're saying.
But anyhow, Shad, it's yeah, even if we'll see what we can do, Shad. I'll try to be more audible still,
So
and I'll
excuse
try
me,
to
sir.
take it
I have a
slow.
question.
Yeah, you said?
I have a question, sir.
Okay, okay, I'm listening.
Okay, you said the more the positive the electrode potential, the stronger the oxidizing agent. So why is magnesium? Why is hydrogen? Why does hydrogen have more potential to oxidize than iron? Hydrogen of only
Why does
one electron at the outermost shell. Why does hydrogen
sorry,
have
I
more
don't.
potential? Okay. Why does hydrogen
Uh-huh.
have more electrode potential to oxidize than iron? Since hydrogen has
Okay,
one electron on the outermost shell, iron has two.
okay. So now, when you talk about oxidation or something that has, if you're talking about why is hydrogen oxidized easily? So now, oxidation is talking about the loss of electron. Oxidation is the loss of electron. So now, if you compare hydrogen now and iron, who do you think would have higher tendency to give off electron?
Iron should have higher tendency to electrode.
I think so. I don't think so.
Okay,
Hydrogen on normal.
but how come zinc has a higher tendency to give up electron than hydrogen?
Okay. The reason why the reason for this is because of zinc now. Looking at its shell structure, if you look at it, it has if you on this thing, it's number 30 on the periodic table.
Yes.
It's number 30, right? You're comparing zinc and iron, right?
Yes.
Zinc and iron. So iron, if we check iron, is we have scandium, titanium, vanadium, chromium, manganese, iron. So iron now is halfly filled. Like after if you look at the electronic configuration of iron, it has half filled, then one extra electron on it, that's paired, one extra paired electron on top. So now this other one, zinc now, it has completely filled electrons, completely filled. Everything is completely filled. So now if zinc wants to give off an electron, it will be easier sort of for it to give off its electron because normally its size is wider than hydrogen size. And remember when we were talking about ionic radius, we said the larger their size, the easier for them to give off electrons. So now it is bigger in size and it's easy to give off its electron. It has a bigger size, so its electrons are loosely held. So compared to hydrogen size, hydrogen is very small because its shell is just one shell. So now comparing hydrogen first with zinc, hydrogen with zinc now. If you look at it now, zinc has a wider shell, so its outermost electron is less shielded. So they can easily steal from it, comparing it to hydrogen. But now when you now compare hydrogen and iron now, hydrogen has one electron in its outermost shell. Iron also has one electron that is kind of paired. If you look at the SPDF configuration now, when you're writing the SPDF configuration of iron, you would write that 4s to 3d5. So now if you look at it now, it has half filled. So it will feel difficult for it to give off that its own electron because now it has almost a stable electronic configuration. So now the more they are stable, the more difficult it is. So it's similar to hydrogen in terms of that it has, I don't know if I wish I could draw the shell configuration because this thing is 26 now. So sorry, not 4s to 3d6, not 4s to 3d6. That's what iron has. So now that 3d6 now that it has, 5 are halfly filled, then 1 is paired. So that one electron that is paired is the one that's supposed to go off. But now something that's already glued with another electron, is difficult for you to remove that one because it's already bonded compared to the one that hydrogen just has one and is not glued to anything. So it doesn't have any extra force that you need to force off that electron from hydrogen. Hydrogen just let it out freely because it's not already bonded to something else. So hydrogen already will want to release that electron. But then this one, the one that it has that's supposed to be free to be given, is already paired with another one inside. It's just like as if you say, I have I'm sure this one will be able to. You have let me say you have someone that has let me say someone that has 100,000 or let me say 10,000 in his account, and someone that has let me say 1,000 in his account. You now say somebody that has 10,000 naira should give off 1,000. The person that has that 10,000 naira would feel difficult to give that his 10,000 naira, break from that is 10,000 naira, because basically you are leaving a round figure and going down to become 4 digits. It's going to be more stressful for you to do that kind of breaking than someone that has just 1,000 naira. You're like, if I lose this 1,000 naira, I don't have anything to lose. Like, I already don't have much, so you can easily give it up. So that's what happens between hydrogen and iron. They both of them have one electron somehow in their outermost shell. Somehow, if you look at it in terms of their SPD configuration, they have one electron somehow. So that's one electron on iron. Now we have I don't know if you are drawing that box stuff that you draw that is like this, that you put 1, 2, 3, 4, 5, then put 1. So that one that is there is one that's supposed to go off, but now that one is bonded with another one. So now it needs to break off this one to give up first before you can start thinking of giving up other ones there. So now, because of that break off first, is making it difficult for it to give. So now the idea behind it is just size, ionic size, and electron pairing already. So that's the reason why that shift is there. So there are still other deeper quantum reasons why these things they behave this way. But on a basic level, this is the reason why hydrogen has higher tendency to give off its electron compared to iron, and why zinc has higher tendency to give off its electron compared to hydrogen. Zinc size is wide, so it's easier to steal from a fowl that has 15 children than she steal from a fowl that has just 3 children. So that was what's happening between zinc and iron, and sorry, zinc and hydrogen. Hydrogen has just one, so it can easily protect that is one if you want to protect. Compared to the one that has plenty, you can easily lose that one. Just like as if I don't know if you are getting the idea. I don't know if you are getting what I'm trying to explain.
Yes, I'm getting it. I'm getting it.
That's just the idea. Someone that has 11,000 naira, you say give me 1,000 naira. The person will give you the 1,000 naira free. That's zinc. Compared to someone that has 1,000 naira, you give it his 1,000 naira out and it will be comfortable because it still has 10,000 naira. But now, someone that has 1,000 naira and someone that has 10,000 naira, say give me 1,000 naira. The person that has 1,000 naira will find it easier to give his 1,000 naira than the person that has 10,000 naira, because that person will be like, would I be breaking this 10,000 naira now to become 9,000 naira? That emotional feeling is something that kind of thing that happens in this kind of state. I don't know if it's clear now.
Yes, yes. No, thanks, sir.
That's just the idea. So there are actually more explanations to the reason for this, but I think this is one that can be more relatable. It has something to do with their electrode potential. It has something to do with their electrode potential, but for that one, the idea behind that, to calculate electrode potential, you need to start using something like standard hydrogen electrode, and the practical explanation is going to be confusing in general sense. It's going to be confusing in general sense, but there is a principle for that. But this is the basic reason behind chemistry, like in general chemistry, this is the basic reason why these kind of things happen. But there are actually other practical that tries to prove why this actually happens in that way. I don't know if I answered your question, Sha.
All right, sir. Thank you.
Yeah. So, um, electrochemical series, as I was trying to explain, someone was talking about the lady that was asking for clarification in regards the ion stuff, in regards the electrochemical series. Just hold on, we'll get there in a minute or in a few minutes. So I said the electrochemical series is a list of elements or compounds arranged according to their electrode potential. So now that electrochemical series that we're seeing now, I think maybe I might send another image later that will show their individual electrode potential. So that way you'll be able to see clearer reasons why. Let me look for that one too. Clearer reasons why these electrons, they have the position that they have, irrespective of their electron on the number of electrons they have and stuff like that. So the arrangement is based on their electron potential and their ability to gain or lose electron. So now, this series helps to predict the direction of electron flow in electrochemical cells and the feasibility of redox reaction. So this electrochemical series can help you to see that, okay, if you have this electrode and this electrode, which one would accept electron, which one would give up electron? When you already know this thing, it can help you tell the direction of electron flow. The more positive electrode, or the electrode with the more positive electrode potential, would be stronger in oxidizing than the other one that is lesser. So I think I will need to send this. I'll send another image to the group. I'll need to send another image to the group. Send another image to the group. I think that way to make the whole thing clear. Let's see. So, sorry.
Yeah.
So I think I'm sending an email. Hey, not.
So,
Yeah, you said?
how does the electrochemical series affect electrolysis or relate to electrolysis?
Okay. For electrochemical series and electrolysis, the series is what I was just trying to explain now. This last sentence, this last two sentences, the more this one I will send it to you, the group now, to make it clear. So as I'll be explaining it, I would like everybody to look at this thing now. So you people will predict by yourself which one would cause, which one would accept and which one would release. And that lady asked the question initially. I think she should pay attention now because this image would clarify everybody on what I was trying to explain. So I just sent the image to the group now. So open the image and let's see what it's about. So on the image now, you will see that it might be small, but I think we just have to manage it like that. But on the image, you will see that magnesium has an electrode potential of minus 237. It has a standard electrode potential of minus 237. So because it is negative, it has more tendency to give off. It has more tendency to give off. The one that has more negative electrode potential has stronger tendencies to give off. The one that is more negative have stronger tendencies to give off electrons. I'm repeating myself. The one that are more negative have stronger tendencies to give off electrons. The one that are negative have stronger tendencies to give off electrons. The one that are positive have higher tendencies to gain electrons. The ones that are positive have higher tendency to gain electrons. So now, in case where you now have a mixture of magnesium and zinc, you already remove the one that. So whose
My
mic is
network
turned
is
on?
very,
Please.
very well.
Someone's mic is turned on and they are watching it. I don't know who it is.
Mba, please
So,
off your mic. Oh.
as your period is biting your brain, you refuse to buy like,
Mba, please off your mic.
Don't worry, I'm using it. So, as I was saying, as I was trying to explain, if you're looking at that electrochemical series now, you will see that magnesium has a more negative value than, which one is the one that is beside itself, than zinc. So because magnesium has more negative value, it means magnesium would give off electron, and the electrode that gives off electron is anode. Shey? Anodes are the positive, and positive give off, right? Hello, can you guys hear me?
Yes, I can hear you, sir.
So just I would like, okay, let me even make it like something that is systematic so that, or structure, so that people can understand very well. So just first off, in your paper, just write anodes, then put bracket open. Anode, bracket open, low electrode potential. Anode, bracket open, low electrode potential, bracket close. Then go to cathode, then write high electrode potential, bracket close. So now the lady that was asking me that, how does this electrode potential help in electrolysis? So now with this electrode potential now, you can be able to tell, okay,
Sir, please don't be
if I
angry.
want,
Can you come again? I did not get you. I had bad network.
okay, I said low electrode potential is anode, high electrode potential is cathode. High electrode,
Excuse me. So what do you mean
yeah,
by low electrode potential and high electrode potential?
that second image I sent to the group, that second image I sent to the group, you will see values that they said something volts, something volts, something volts. So those are the volts that we're talking about. Those volts are the electrode potential. So you will see mg, like mg2 plus slash mg, they gave a value minus 237V. That is its electrode potential. They said zinc Zn2 plus to Zn, bracket open, minus 0.76 volts. That is its electrode potential. So each of these ions, the electrode potentials are listed beside them. So now we can now tell that, okay, if we now have say we have silver and bromine, or let me say two electrodes, silver and copper, which one will be the anode? Which one will be the cathode? So now they're now asking you which one would be the anode, which one will be the cathode. From looking at the electrochemical series, you look at it, okay, which one has the lowest electrode potential between copper and silver? Which one has the lowest electrode potential? Someone should tell me from the class. Between silver and copper, looking at that electrochemical series, which one has the lowest electrode potential?
Copper.
Copper.
Copper has the lowest. So meaning automatically copper would be the anode and silver will be the cathode. I don't know if it's making any sense now. I don't know if it's making any sense because of we've looked at it. We compared copper and silver. Now they are the two electrodes they are giving us. Say,
Yeah.
okay, they told you you are a chemist, you are a chemistry student. If I gave you copper and silver, which of the electrode, as for electrolysis, which of the electrode should be the positive electrode and which of them will be negative electrode? You just say, okay, no problem, give me the electrochemical series. You look at it, okay, this is the order. That means since silver or since copper has lower electrode potential, it means it will be the positive one. Then silver has the higher electrode potential. That means it's going to be the negative electrode. So because of that, now this is going to be the positive and this is going to be negative because of the result of their difference in electrode potential. So that's the simple answer to that question. So the electrochemical series can help you to predict which electrode would be the positive or which of them would be the negative. Or in other words, it will tell you which of them would electrode leave from and which of them would electrode come to.
Okay, sir. So the cathode, the electrons that go to the cathode, it must not be negatively charged.
The cathode is negatively charged. So the electrons that are coming to it, they are going to be these ions, not electrons. The ions that will come into the cathode will be positively charged because the cathode is already negatively charged. So like poles repel, unlike poles will definitely attract. So the unlike pole negative would always attract positive. So if you have a negative electrode now, it means the positive species would get attracted to that negative electrode. So even if we had two positive, the one that has what they call it, that is more if you look at this same electrochemical series and you look at the one that which one of them is more behaving like a positive electrode, the one that is behaving more like a positive will go to that place, the one that is behaving more like a negative will come to this other place. I don't know if it's making sense. The series will tell you which one is more negative, which one is more positive, or which one has more tendencies to gain electron and which one has more tendencies to accept electron. So on the negative electrode, what happens on the negative electrode is reduction occurs on the cathode. So meaning on the cathode, the ones that have electrons to give off would always come to the cathode. Or the ones that have more tendencies to give off electron would come to the cathode. Okay, write it like that. Under that cathode, right, it attracts, under cathode, right, it attracts ions with, it attracts ions with, what would I put it now? How would I put this in English now? The cathode attracts ion with higher tendencies to give off electron. It attracts ions with higher tendencies to give off electron or ions with lower electrode potential. So it attracts electrons, it attracts ions or species with higher tendencies to give off electron. And it has that, or in other words, the ones that have high lower electrode potential. So looking at it now, we know that if we have, using the extremes now, if we have magnesium and, or let me use the second to the last extreme, we have zinc and oxygen. If you say, let's assume we have zinc electrode and maybe oxygen electrode, for some reasons, oxygen happens to be the electrode, zinc and oxygen connected together, we know that automatically zinc would be the positive electrode while oxygen will be the negative electrode, right?
Yes.
Zinc will be the anode while oxygen will be the cathode. So now this anode and cathode now, they would attract the opposite of them. So the one that has the lowest, the highest electrode potential will attract things that have lower electrode potential to itself. And the one that has lower potential electric potential will attract things that have higher electric potential to themselves. So now, assuming the system was comprising of magnesium, zinc, oxygen, fluorine, magnesium, zinc, oxygen, fluorine. So the zinc electrode and oxygen, the zinc and oxygen are the electrodes. But in the solution now, we now have magnesium and iron and fluorine in the solution. So now the oxygen would attract the magnesium, while the zinc will attract the fluorine. I don't know if you are seeing the flipping there. So everybody, that idea of like poles will repel and unlike pole will attract is still playing in here, because zinc and magnesium, they are close, so they are somehow like as if both of them are the same, so they will not want to stay together. It's like as if it's not balanced, like boy and boy staying together. It's not making sense. Boy would always want to stay around a girl, and a girl would always want to stay around a boy. So that's just the same thing that's happening here. So the ones that are at the extreme would always want to attract the ones that are on the other extreme, while the ones that are on the other extreme will always want to attract the ones on the other extreme. So that's just how it works. I don't know if you are getting the picture already. Hello.
Yes, sir.
Yes, sir.
Okay. Does anyone still have any question? Probably I could look for a simpler explanation to it. The lady asked the lady asked for the use of electrochemical series and in electrolysis. I hope I've answered the question. And the one that was asking
Sir,
for magnesium.
I'm confused more.
Did you write what I was saying you should write?
Yes, I did.
When I said anode attracts, anode is the one that it attracts this, and anode is this. Did you write it down? Can you hear me?
Yes, I can hear you.
Sit down, right? Did you write it down? I don't know. It seems like a network is having issues, Sha. In this kind of issue, in this kind of situation where I'm trying to explain something, and if your network is distorting, I don't really know what to do. I don't really know what to do. So I think maybe the best that can happen, maybe as the class is going on this week, before this week runs out, by tomorrow, I think the night class for today will be ready. But I don't know, the upload will be happening probably by weekend for this entire week, because all the videos for previous night class are ready already. So by this weekend, night class of this week will be uploaded. So probably if you did not already, or you happen to have been having network issues, just the video would be available by weekend. The videos for the entire week night class will be available by weekend. So for those people that probably are having distorted network, so such that we can be able to cover more ground. So let's see whether we can move forward in this.
Can I ask my question?
Okay, ask a question. If you can, if your just ask a question. Because I know just ask a question. Let me just see whether your network will be clearer now. Hello? Hello, in case you are hearing me, I'm not hearing you. We are not hearing you on the call.
Okay, you said that anode is positively charged and low
Yes.
and ions with a low electric potential will go to anode. Is it
Ions with high electrical potential will go to the anode.
okay? Okay,
So the reverse case for cathode. Everything I said for anode, the reverse is the case for them in case of cathode.
okay.
So that's just it.
How do I recognize those that have low electrode potential and those that have high electrode potential? I mean the ions.
Look at the image, the second image I sent to the group. If you can see the second image, I sent to the group. Just know that the ones on the right hand side have high electric potential. The one on the left hand side have low electric potential. The second image will tell you from all those numbers you're seeing, the ones on the left, their values are negative, so they have low. The ones on the right, their values are positive, so that they have high. So that's how you would find out that.
Okay.
Okay, so we can move on now.
Yes.
Okay, so now let's move on. We've explained that the more positive electrode potential are stronger oxidizing agents, while the more negative are stronger reducing agents. So it's just the same thing I'm saying, but just in different terms. So moving to electrochemical cells. So
Repeat what you said now, please.
I just repeated what was on this screen. I said the more positive electrodes are stronger. The more positive the electrode potential, the stronger oxidizing the particular electrode will be. And the more negative the electrode potential, the stronger the reducing agent the electrode will be. So these things I'm saying, the things that I'm just reading off word for word what's on the slide. So probably after the lesson,
All
we'll
right.
see
All right.
it there, so we could be able to cover up the whole lesson. So we'll not have to have a postponement of the class or half class. Let's hurry up. So next we have electrochemical cells. So for electrochemical cells, at the beginning I said everything, both electrolytic cell, galvanic cell, they are all electrochemical cells. Electrolysis so happens in electrolytic cell. So, but there are majorly two types of electrochemical cells. So there are two things I'm mentioning. And there is one thing I'm mentioning that is like the umbrella covering both other things. There is electrochemical cell. That's the main deal because we're talking about electrochemistry. Electrochemistry, electrochemical cell. That's the name of all the types of cell. That's the general name for all the type of cell. So now under electrochemical cell, now we now have two types of electrochemical cells. The first one is a galvanic cell. The second one is an electrolytic cell. So we have two types of electrochemical cell, galvanic and electrolytic cells. Two types of electrochemical cell. We have galvanic and electrolytic cell. So now I'm trying to explain now what the differences between galvanic and electrolytic cells are. So galvanic cells are cells that they convert chemical energy to electrical energy or chemical energy to electricity. They convert chemical energy into electrical energy or into electricity through spontaneous chemical reactions. Through spontaneous chemical reactions. Or you can put it instead of true, you can put as in spontaneous chemical reactions. I think in is the better word. In spontaneous chemical reaction. So examples
Please
of this
give the definition again, please. Galvanic cells are
galvanic
those
cell,
the cells that convert chemical energy to what?
electrical energy or electricity. So electrical energy or electricity in spontaneous reaction or in spontaneous chemical reactions. In spontaneous chemical reactions. So while electrolytic, now not electrochemical, electrolytic cells, they are um, cells that convert electrical energy into chemical energy or to cause they convert electrical energy to cause chemical reactions. So they move from electrical to chemical. Electrical energy to cause chemical reactions. Electrical energy to cause chemical reactions. Electrical energy to cause chemical reaction. That's electrolytic cell. So in non-spontaneous reactions, in non-spontaneous reaction,
Please, can I have the
I don't know if you
definition
have
of electrolytic cell?
electrolytic cells are cells that convert electrical energy into chemical energy. Convert electrical energy into chemical reactions, into chemical reactions in non-spontaneous reactions. In non-spontaneous reactions. So here I gave examples of these two
So
cells. I
please
said
come
for the
again.
first one we have oh, electrolytic cells are cells that convert electrical energy into chemical reactions in non-spontaneous reactions or for non-spontaneous reactions.
Thank you very much.
Yeah, so examples now we have examples of galvanic cells. We have batteries. So batteries are examples of galvanic cells. While for electrolytic cells, we have electrolysis. Electrolysis cells that are, or electrolysis, just put as electrolysis. Because electrolysis uses electrolytic cells. So now, batteries, just now, right by the side now, galvanic cells don't need batteries because they are batteries, obviously. Galvanic cells don't need batteries, obviously, because they are batteries. That you might not write that obviously because they are batteries, but galvanic cells they don't need batteries. While electrolytic cell need batteries. Electrolytic cells need batteries. So now I'm trying to mention some of the distinguishing factors aside their definition. So galvanic cells they don't need battery, while electrolytic cells they need battery because it's the battery that forces the reaction to happen. While for galvanic one they don't need any forcing, they don't need any force. They operate or they form their reaction by themselves without any external application. So that's the two types of electrochemical cells. I don't know if that is clear.
Yes,
I
sir.
hope so. Yeah, so having mentioned these two types of cell, there is what we know, there's what is known as standard electrode potential, which was what I was trying to explain before. So now this is where we will talk about the what standard electrode potential refers to. So first off, we'll talk about EMF before going to standard electrode potential. So EMF has a definition that says that it is the potential difference between two electrodes in an electrochemical cell. It is the potential difference between two electrodes in an electrochemical cell. So they do not specify whether it's the galvanic cell or electrolytic cell. So it is the potential difference between any two electrodes in a particular cell. Any two electrodes in any particular cell. The potential difference between them is the EMF. So while the standard electrode potential is the potential of an electrode relative to standard hydrogen electrode under standard condition. So now that standard electrode potential, it is the potential of a single electrode or of a particular electrode when you compare it with standard hydrogen electrode, SHE. So standard electrode potential is the potential difference of a particular electrode when you compare it to the standard hydrogen electrode. So standard hydrogen electrode is an electrode that they use to get that it has a zero value. It has value electric potential of zero. So because it has that zero value, it can be used as a standard to gauge other ones. If you look at it, hydrogen on that electrochemical series that we showed, the electric potential was zero for hydrogen. So because of that reason, they made hydrogen a standard for measuring every other one. So anything that is higher than hydrogen will stay on one side. Anything that is lower than hydrogen will stay on the other side. So they always use hydrogen to be as a gauge, and they call it standard hydrogen electrode. So they use it to get the standard hydrogen, they use to get the standard electrode potential of any electrode at all. So they will use the standard, they use the She electrode and any other electrode Then if the she electrode accepts electron, they'll say, okay, she electrode, since it's accepting electrode, that means it is negative, and the other one is positive, okay, it will have so and so value. So if this one is positive, just that idea, they use it as a standard to gauge other ones, whether they will be greater than she or less than she in terms of gaining electron or losing electron. So that's just the idea. So the more positive the electrode potential or the standard electrode potential, the greater the tendency to gain electrons. So this is what I was explaining before. I said the higher the value of this thing, the higher the electrode potential value, the higher the ability to gain electron. The higher the electrode potential value, the higher the ability to gain electron. That's what I was trying to explain before. In that time, I was explaining the electrode potential table. So that series, electrochemical series. So the higher the value, the higher the ability to gain electron. So the higher the value, the more positive, the more the tendency to gain electron. I'm saying the same thing. So the
Huh?
higher the value, the more the tendency to gain electron.
You
Yeah.
mean the she? Are you referring to the
The
she?
what?
The
No, not the sheep. I'm talking
standard
about
type.
generally. I'm talking about
You're talking
generally. Generally.
uh-huh.
Generally. Any electrode that is more positive any electrode, the more ability, the more positive the electrode potential of any electrode, the more tendency that electrode has ability to gain electron. The more positive a particular electron, the more strong it is to gain electron. So that's just the idea. So now moving on, there is an equation that is called the Nernst equation that makes use of the standard electrode potential of electrodes to determine the electrode potential at a particular time. So standard electrode potential is the potential in comparison to
Excuse me, sir.
hydrogen. Yeah, I can hear you.
Excuse me, sir. Please, you said the
Yeah, I'm listening.
more positive, you said the more positive an electrode is, the more what? I did not get that.
The more the thing is, the more stronger it is to gain electron. So just like as if
Thank you, sir.
the more muscle you have, the more you can pull something to yourself, the more you can bully people to collect what they have. The more muscle you have, the more you can bully people to collect what they have. That's just the idea. The more positive a particular electrode's potential is, the more its ability to collect other people's electron. That's just the idea. The more positive an
Thank you, sir.
electrode is, the more positive it has, the more tendency it has to pull other people's electrons to itself to gain electron. So now we have the next equation. So this equation is used to determine the electrode potential that is not the standard electrode potential. So it can be used to determine the electrode potential of any particular electrode at any given concentration at all, because the standard electric potential is the potential at a specific standard condition. It is the potential at a particular standard condition. So now, if that standard condition is altered, to get the electric potential at that point, now you need to use the next equation to get the electric potential, because now it has left standard level. It has gone to something that is not standard. So now to get the electric potential, you need to use the next equation to get the non-standardized electric potential. So this is the formula here. This is the formula for the next equation. E being the normal electric potential on non-standard cases, E naught being the standard electric potential, then R being your gas constant, T being your temperature, N being your number of electrons, F being your normal Faraday's constant 96500, then Q being the reaction quotient. The reaction quotient. Just most of the time that they will give you in the reaction, or sometimes they will give you in terms of concentration, but in this level it's just for reaction. So basically, this is, I think, third level chemistry for people that are studying chemistry. Going deeper into this thing is third level chemistry. So the next equation is basically this. So just memorize the
Hello, sir.
formula.
Hello,
Yeah,
sir.
I can hear you. Yeah, I can hear you.
Please, I need more explanation on that next equation. You explain something, and that thing you explain is very important. We need to get it right before the equation. Don't vex, please.
Okay, I said the next equation is just used. It is only used to get the what they call it, potential of any electrode when the conditions are not standard. The next equation is used to get the potential of any electrode when the conditions are not standard conditions. So that's what I was trying to explain, and I was trying to use what in. So
Okay,
next equation
thank
is
you.
used. So in case you see it somewhere, that's just the purpose of the next equation, to get the electric potential of any electrode when it's not under standard condition. So now this is an example that could be under next equation. They said calculate the EMF of a half cell at this temperature with this concentration of copper and this concentration of copper. Copper ion has this concentration, copper molecule or
Sorry,
copper
sir.
atom has this.
Sorry for drawing you back. I just missed one word. Please let me just give you what I that the next equation is used to get the potential difference of any electrode when the words are not under standard condition.
When the conditions are not under standard conditions. When the conditions are not standard.
Okay.
So now this next equation now, as I was trying to explain, I was saying that this equation now, this Q can be given, but in some cases, I said in some cases, it's given to you as concentration. So now, I would like you to write this on your this thing in your notes. Then write after you've written this equation now in your notes, write or write or then write this same everything up until this point here. Everything, write everything here up until this in. After in, just wait. Write everything until when you get to this in, then wait. E equals to E naught minus RT over NF times in. So when you reach that in, just wait. I'll just give like a few seconds, then I'll call what's supposed to be there instead of Q. So in cases where you are not given Q, there is a way to get the same Q value. So if you've gotten there now, for those people that have gotten there now, it will now be in bracket open. That is this in bracket open. You now write above, like the numerator. You write ion concentration over atom concentration. So that Q, you replace Q with ion concentration over atom concentration. So instead of Q in this equation here, instead of Q, you put ion concentration over atom concentration. Instead of
So
Q, you put ion
it
concentration.
will now become
E
times in.
equals, yeah, E equals E naught minus RT over NF times ln bracket open ion concentration over atom concentration bracket close. That will be the formula. So that's the alternative formula that how it can be like in another case. So now that is the one that you would apply in this case now, because now they did not give you the Q value. So now, but they gave us ion concentration. So this is the ion concentration here. Then this is the atom concentration. So atom does not have charge, while ion has charge. So now this one will be the one up. You just plug everything inside the formula and you get your final answer. Plugging everything inside the formula, you get your final answer. Our N is 2 because of the charge of copper is 2. As I said before, the charge of copper, the number of electrons that are released when you convert copper atom into copper ion, the amount of electrons that are released is 2 electrons. So the N value is 2. So solving that, you get your answer to be 0.3696 volts as the EMF or the potential of the electrode under this particular condition. So I think time is already run. Okay, we still have a few minutes. And let me see. Oh Lord. Okay. So
Sorry, sir, I have a question.
Yeah, I'm listening.
There's Faraday's law there, like the constant. Is it also
Yes.
included in the solution? I can't see it there.
Okay, they made all these things like constants here. They made everything here constant. They simplified everything here. This RT over NF, they found the value and simplified everything. RT has a constant value. R has 8.314 here. Is a constant, universal gas constant, 8.314. Faraday's constant, T, they gave us temperature as 298. Then N is 2. That's why you see 2 here. Then this F. So RTF has a constant value when the T's value is 28. This is, but instead of doing it that way, just put everything you need that they gave you from the question one by one, and you will still get the same answer. So don't, even if you don't see it here, this one was just a short form to write it. But even if you don't see it here, just know the formula and apply the formula. If you apply the formula, you still end up where I got what I got. You still get what I
Okay,
got.
sir.
Yeah. So just know that the N is 2. And the reason why it's 2 is because copper gives off 2 electrons. So 2 plus, copper 2 plus, that 2 plus is telling you that copper gave off 2 electrons. So now, moving forward, we have fuel cells.
How did you get that log 0.1 over 1?
Use lane. Use lane. Just use normal lane. Just use normal lane. If you use normal lane, just confirm that my own answer is correct. Use normal lane. If you should use normal lane, you will get the answer. If you don't use, if you want to use change lane, lane has a value to log. Lane is equal to 2.303 log something. Lane is 2.303 log something. So they simplified everything and put it into this expression here. So don't, instead of looking at what I did, just use the same thing that is here and solve. You will get the same answer I got.
Okay.
Once you do that, you confirm the answer. The answer should be the same with my own. So let's hurry up to what we have now.
So excuse me, sir.
Once we, yeah,
Sorry, you in the formula you didn't you didn't use the Faraday's law, the value for the Faraday's law while solving. You please keep it.
yeah, that's what I'm saying. I said they simplified everything. If you look at it in the solving, the lane changed from lane to log. So I converted the lane value from lane to log. So I used 2.303 log. Then R is 8.314 times temperature 298 all over 2 times what they call it, our Faraday's constant 96500. Solve that one as thing is. Just try using the formula that I gave and get your answer and
All
see
right,
whether
sir.
we are the
I
same.
understand.
Yeah.
All right, sir.
Because they solved everything and they put it inside, but just that this is the simplified form of the whole thing, just for simplicity. So you might see it like this in some textbooks where they will use log instead of lane, but it's still the same thing. Or they might even put this constant 0.0592 all over n. That's what they will do in some textbooks, 0.0592 all over n log something, something, something. But it's still the same thing. Some textbooks say 0.0593. It's still the same thing.
Is it 593 or 693?
Which one?
I think it's 69. That's in now.
No, in is not 693. Oh. In is two. Lean is equal to 2.303 log anything. Lean anything is equal to 2.303 log anything. So just I don't want to bring confusion here. That is the reason why I'm saying just use this input formula straight up. You will get the same answer. Don't worry yourself or trying to just you will get the same answer.
Okay.
So if you should do that, you should get the same answer with me. So now I would like somebody to just look at this fuel cell and tell me what type of electrochemical cell fuel cell is. Look at the definition I have here under fuel cell and tell me what type of electrochemical cell fuel cell is.
Electrolytic cell.
You said?
It's
It's an
galvanic
electrolytic
cells.
galvanic cell, sorry.
It's
It
galvanic
converts
cell.
it's galvanic.
Okay. So it's galvanic because it converts chemical to
Chemical
electric.
energy into electric.
Yeah. So that is fuel cell. It's the kind of cell that converts chemical. It's just a type of voltaic
Uh,
cell
uh,
or
it's,
or galvanic. It's a type of galvanic cell.
it's a type of galvanic cell. Okay.
Yeah, so it's the type of galvanic cell. So example, we have hydrogen fuel cell, and this particular one uses hydrogen electrode and oxygen to produce electricity and water. So those type of cells are called fuel cells. So fuel cells is typically a particular cell that is made up of water, hydrogen, and oxygen. So it's made up of water, hydrogen, and oxygen. It's a very, very safe kind of cell because other ones they will contain metals, they will contain, and metals can be poisonous. But fuel cell is just made up of hydrogen, oxygen, and water. So it's one of the best type of electrochemical cells so far because that's no pollution at all. So they are very efficient and environmental friendly because they produce no pollution. So this is why they are they are considered to be environmental friendly, and they are said to not have pollution because they are made up of just these elements, and these elements are not harmful to the environment. They are already present in the environment. So that's for fuel cells. So now this is example. This is the overall cell reaction of a fuel cell. This place here is the overall cell reaction of a fuel cell. It's made up of hydrogen,
Can I
oxygen, and
ask a
water.
question, sir? Can
Yeah,
I
I'm
ask
listening.
a question?
Yes.
Concerning the pollution, is it that it don't have it has low pollution or no pollution at all?
No
Because
pollution
the
at all.
reaction, okay, the reaction of the water, hydrogen, and oxygen, it won't produce any pollutant at all.
Yes, it does not produce any harmful stuff. So this is the reaction here. Just hydrogen gas reacting with oxygen gas to give you water. So water is not harmful. Hydrogen gas is not harmful. Oxygen gas is not harmful. They are always present in the air. So these kind of cells, they are known as fuel cell. So this fuel cell, it's important that you should note this anode reaction and also the cathode reaction. Anode reaction and cathode reaction. Just memorize it for knowledge sake. So memorize these things here for knowledge sake. These things here. So this is the typical fuel cell. So now moving on. Under batteries, batteries is also another type of
Sir, please, I
electrochemical.
want
Sorry.
to.
Okay. So I can move on now. So under batteries now, we have battery is also a type of galvanic cell. Fuel cell is a type of galvanic cell. But now batteries now are of different size types that are not fuel cells. So these types that are not fuel cells, batteries are the electrolytic cells. Sorry, Batteries are galvanic cells that are not fuel cells. So batteries are the galvanic cells that are not fuel cells. So galvanic cells can be seen as fuel cells and batteries. Galvanic cells can be seen as fuel cells and batteries, either of the two. So when it's not a battery, next thing it is a fuel cell because we have just fuel cell and battery cell under galvanic cells. So every other type of cell that's not a fuel cell is a battery, so long as it so long as it's a galvanic cell. So now under these batteries now we have two types of battery. We have primary and secondary batteries. Primary and secondary batteries. So the primary batteries, they are called primary because they are non-rechargeable. They are non-rechargeable. While the secondary batteries, they are called secondary because they are rechargeable. They are rechargeable and they are made up of typically mostly lithium ions. So like this our current day battery now that is in our phone, 5000 mAh. They are usually lithium ion batteries. So the reason why they are rechargeable is because lithium ion is one of the smallest ion that exists, one of the smallest. So it's easy for them to move through their membrane and for charging. Because when charging happens, I hope you guys know that the more you charge your phone, the more the battery spoils. So if possible, anything you can do to minimize charging a particular phone's battery would help to extend the life of the battery. And some people, some scientists, they said it's best, or some people that have studied, they said it's best that you should keep your battery within the range of I think 80% to 20%. Once your battery gets to 80%, don't allow it to get to 100 most of the times. Once it gets, you can make it get to 100, but sometimes it's just if you want to get the best efficiency of the battery, which we might not notice it as Nigerians because we use phones for a very long time. So the best practice for using batteries, once the battery gets to probably 80, 85, 90%, just detach it and start using it. And don't charge it again until it gets down to 20, 15%, that same range. Then you can charge it again. Don't be charging it when it's in between. Don't be charging it and be using it during those procedures. There are things that can help to damage the battery if you don't follow them. So we have rechargeable, we have primary batteries and secondary batteries. So and primary are non-rechargeable, secondary are rechargeable. So now battery is where you would see the basic what they call it Ohm's law. V equals to IR or I equals to V over R. So sometimes you might see instead of V, you see it as EMF over R. So E is seen as V, E representing the EMF. EMF is seen as a potential difference, and that is the same thing as V, potential. Similar, but the potential difference is when it is not opened, when the battery is not giving any current to any external circuit. But anyhow, the idea is that the formula it uses Ohm's law. I is equal to V over R. So to solve. So this one's a basic question that if you see it, you should just be able to know. They ask you find the current, you will check, okay, current. Does it have, do they give us potential? Yes. Do they give us resistance? Yes. So yeah, so use current formula, Ohm's law. So these ones are just cheap stuffs. I think that
So
should be all.
in this equation now, what does E stands for?
Is the EMF. EMF.
Is it
That's the voltage.
the electromotive force, EMF?
Yes. Yes. Yes.
All right. All right.
So that is for the lesson of today. That's all for today's lesson. That's all for today's lesson. I don't know if anyone
Thanks
has
a
any other
lot.
question.
You have done noble.
Does anyone have any other question before we call it a wrap? Question. Okay. So thank you all for attending today's lesson. And as usual, I wish you guys best for your exams. I wish you guys best for your exams. So see you guys when I see you on
Thank you.
see you guys when next we see. Good night, everybody.